In section 4.5, we're going to be looking at 2x2 matrices, their determinants, and their inverses. So there's a couple of things that we want to do. In this part 1 of this video, we're going to look at the determinants and how to find the inverse. Then in part 2, we'll look at how to use the inverse matrices to solve a matrix equation. All right, so let's start with a couple of just vocabulary terms that we need when we talk about matrices. We're going to talk about the multiplicative identity matrix. And for a 2x2 matrix, that matrix looks like this one right here, where I have what we call the main diagonal, okay, which starts up here in this corner and comes down this way. And then that has ones and then zeros everywhere else in the matrix. So for a 2x2, it looks like this. You have ones on the diagonal and then zeros in the other two places. This is called the identity matrix, and this is like any other identity. When I multiply this matrix times another matrix, it will give me the original matrix as my answer, right? It's like multiplying by 1. This is the version of that you'd need for a matrix. We also have in matrices a multiplicative inverse. And like other parts of matrices, there are some that have inverses and some that do not. So in order to tell if it's an inverse, you have to be able to multiply the matrix together and get the identity matrix I as your product. And since multiplication in a matrix is not commutative, we actually have to prove that it works both directions for the multiplication. So we have to prove that A times X and then also X times A makes that the identity matrix. So in our case, since we're working with 2x2 matrices today, that's going to be this matrix back up here with the ones in the diagonal. And then the notation that we use to show that it's an inverse matrix is we use the name of the original matrix. In my case, it was A, and we use this little -1 symbol up here. So that's saying the inverse of matrix A. So if I multiply A times its inverse, I will end up with this identity matrix up here. Okay, so let's look at how that actually works by showing that these two matrices are inverses of one another. So what should happen if they are inverses is that I should be able to multiply them together and end up with that identity matrix. And then I'll have to, like I said, to prove it, I will have to make sure that I do that both A times B and B times A. All right, so let's do that real quick. Let's do A times B. And if you remember your matrix multiplication, we're going to multiply rows by columns. So when I do that, I will end up with the first row and the first column. 2 times 2, 4. 3 times -1 is -3. 4 -3 gives me 1. Again, do the same thing on the next one. We're going to do same row, but with the second column. So 2 times -3 is -6. 3 times 2 is +6, -6 and +6 make 0. Okay, then we move on to the second row, just reviewing our multiplication here. 1 times 2 is going to give me 2, and 2 times -1 is -2. So 2 and -2 make 0. And then lastly, with the second row here and the last column, 1 times -3 is going to be -3, and 2 times 2 is 4. -3 and 4 gives me 1. So when I multiply these together, I do get the identity matrix. Now, if that's the case, most likely it's going to be the case that B times A is the same matrix, but we want to make sure. So this time I'll be multiplying the opposite direction. I'll be multiplying B first times A. So I'll be using the rows here and the columns over here. So maybe I'll just circle those this time since I'm not going to rewrite them. We'll just write them this way. So we'll do the rows and the columns the other way. So this time it's 2 times 2 is 4, and -3 times 1 is -3, so 4 and -3 is 1. Then we stick with the first row and we go back for the second column here, the 3 and the 2. 2 times 3 is 6, -3 times 2 is -6, so that is again 0. Now we're going to go down to the second row, finish up our multiplication. -1 times 2 is -2. 2 times 1 is +2. That's going to give me 0. And then in the last column, -1 times 3 is -3, and 2 times 2 is 4. -3 and 4 make 1. So by showing that the multiplication both ways, A times B and B times A, gives me the identity matrix, then yes, these are inverses. B is the inverse of A is the inverse of B. Okay, so now that we know what an inverse is, we need to know a couple of things before we can actually find the inverse. And one of the things that we use to find an inverse, and even to tell us if there's an inverse that's going to exist for that matrix, is called the determinant. And the determinant in a 2x2 matrix is pretty easy to calculate. All we have to do, if you look at the formula here, if you look at my formula, it says A times D minus B times C. So when you look at the matrix itself, you can visually picture this. A times D, so I'm going to multiply that main diagonal together first, and then I'm going to swap and go the opposite direction, B times C, and I'm going to end up with A times D minus B times C. And it's that simple to find your determinant of a 2x2 matrix. So in my two examples here, right, I'm going to do the main diagonal first. -3 times -5 is +15. And then do the opposite diagonal next. 4 times 2, so -4 times 2, whoops, which is going to be 8. So 15 minus 8 tells me that the determinant of this is 7. Okay, now, so let's do a second example. So main diagonal first, 8 times 3, 24, 7 times 2, we're going to have 10. Sorry, try that again. We're going to end up with 10. 14 equals 10. So 24 minus 14 is 10 is my determinant. So what does the determinant tell me though? Okay, well the determinant tells me, first of all, whether or not there is an inverse. Okay, so if the determinant is anything but 0, then the matrix has an inverse. Okay, the only time you will not have an inverse is if the determinant is 0. So you're going to need to find the determinant before you can find the inverse. Then once we find the determinant, we might as well find it first so we know if we have an inverse. And then once we find it, we're actually going to use it to calculate the inverse matrix. We're going to use it as part of a scalar that we're going to use to find the inverse. So we got to do a couple of things to our matrix. You'll notice if this is my original matrix over here, A, okay, it goes A, B, C, D, just like we did before. You'll notice when I come over here, do you notice that these are all sort of rearranged here? What happens is you swap the numbers in the main diagonal and you make the other diagonal into their opposites. Okay, so B and C stay put, but you change their signs. A and D trade places. And then you're going to use your determinant as part of a scalar that you're going to multiply by when you're finished. Okay, so let's look at how that works. First of all, like I said, we need to find the determinant of our matrix. So let's find the determinant of our matrix M here. So to find the determinant, I'm first going to take my main diagonal. So -4 times -2 is 8, minus the other diagonal, 5 times 2 is 10. 8 minus 10 is -2. So my determinant is -2. That tells me that there will be an inverse to this matrix. So I'm going to use that determinant then to find the inverse. So we're going to find M inverse. And we're going to do that by taking 1 over the determinant. So my determinant was -2. It's going to make my scalar -1/2. And then remember, we have to rearrange the elements of my matrix. So the main diagonal, they swap places. Okay, remember, go back and look at my original matrix for M. And then the other diagonal, they don't swap places, they change signs. So 2 becomes -2 and 5 becomes -5. So what I want to do with this then is simplify this out so that I have just my matrix. In other words, I want to do the scalar multiplication. So M inverse is going to be equal to, we just take a -1/2 times everything, +2, +1, +5/2 or 2.5, and +1 again. So this matrix, 2, 1, 5 halves, and 1, would be the inverse of the original matrix M. So this is going to be the inverse of my original matrix that I had up here to start with. Okay, so that's the inverse of that matrix. So it's going to be important when we get to the next part of this section that we actually know how to find the inverse of a matrix first. All right, so let's practice one more time with n. So on n, I want to check my determinant first. So I'm going to do main diagonal. Let's do determinant of n. The main diagonal is 3 times 6. That's going to be 18. The opposite diagonal is 2 times 9. That's also 18. 18 minus 18 is 0. So anytime I get a determinant of 0, there is no inverse. You can say does not exist. Okay, does not exist.